Okay, so today we're gonna continue with SVMs just really quickly, and then we're gonna move on to unsupervised learning, which is a whole different paradigm. So if we recall from last class, we said that there's this other way to write the optimization objective of SVMs, of soft margin SVMs, using Lagrange multipliers, which is outside of the scope of this class, but you learn it in Calculus 3, which is not a prereq to this class. And so, yeah, you don't need to understand how we get there. Just know that doing some calculus and algebra and optimization and math, this is the same thing as what we derived before. And the key observation where we ended last class was that all of these terms are scalars except for x transpose x, where xi is one data point and xj is the other data point. And so if we're scaling our data into a high dimensional space, which recall last class we said that if we have data that's non-linearly separable in a low dimension, we can increase it into a higher dimension. So this is, for example, x and x squared, where the data is not even close to being separable in the low dimensional space. There's no linearly separable. There's no point in this place that's going to separate the two categories. But if we project the data into a higher dimension, for example, by adding a second dimension that's x squared, which would look perhaps something like this, then all of a sudden in that higher dimensional space, it's possible to find a linearly separating hyperplane. But the problem is, as we talked about last time, sometimes it requires expanding into really, really high dimensional space. And that's going to be impossible to store on a computer. Even if we could somehow store it, the calculation would be really expensive. And so it's not feasible to increase our data into these high dimensions. But we made this key observation that the bulk of the computation is this dot product. And so the kernel trick, which I think we ended last class on, the kernel trick is where we calculate, or maybe calculate's the wrong word. We find a kernel, which is basically a function, kernel function, which tells us what the dot product would be in a higher dimension without requiring us to convert the data into the higher dimension and calculate the dot product. And if we recall from the quick linear algebra review of last class, a dot product is always a scalar. So for example, dot product of a1 comma a2 of that vector dot this vector is equal to a1 times b1 plus a2 B2 plus A3, B3. So that's a scalar. So no matter how high dimensional your data are, when you take the dot product of the two vectors, you get a scalar, so a number at the end of that. And so if we could find a nice kernel function that can tell us what that dot product would be if we had converted the data into higher dimensions, then we can save all this computation and get the advantage of solving this optimization problem and knowing what this dot product is going to be without requiring us to convert the data into a high dimensional xi and xj that's not going to be able to be stored on the computer. So let's see an example of that, and I think it'll be clear how this works. So there's many different kernel functions. We'll just talk about one today, and you can check out other ones as you wish. So a pretty popular one is called the polynomial kernel, and we'll use k of ab to denote it. And that function is the dot product of a and b plus r to the dth power, where a is data point number 1, and b is data point number 2, and r and d are hyperparameters. So if you're using the kernel, the polynomial kernel, you'll set r and d. D happens to tell us the dimension that we're going into. So D stands for two things. Stands for the degree of the polynomial. It also stands for the dimension of the space that we're converting our data into. We won't derive this kernel, but just to see an example of how it works, let's say that, I think this will be really clear when you see the example. Let's say that we set r to be 1/2 and d to be 2, and let's say we're working with one-dimensional data. So a dot product b, but when they're one-dimensional, it's just a times b plus 1/2 to the second power. Doing a little bit of algebra. Comes out to be this. So a squared b squared plus ab plus 1/4. And the observation is that that is also equal to this dot product. So that is equal to that dot product. So basically we're saying that if we had converted A into a higher dimensional space with A as one axis, A squared as the second axis, and 1/2 as a third axis, and same thing for B. If we take the dot product of that higher dimensional space, we get the same value as the kernel. And so thus xi squared 1/2 is the coordinate in the higher dimension. And to see that visually, it might look like the new coordinate space that we never actually have to convert our data into is similar to what I showed before, but 1/2 is a constant, so we could ignore it. This dimension is a constant, so we can ignore.
The second vector is transpose, or?
Yeah, it's transposed. I'm just drawing it. Yeah, so technically this A vector should be like that, but I'm just drawing it in list notation. Yeah. Let's just do another example. Yeah, I mean, I could do that just to be mathematically rigorous. Another example. So if we wanted to see it go into 3 dimensions, where our original data is 1-dimensional, it's the same thing. I'm not going to do all the math for you, but using the same math as before. Just algebra, that comes out to be this, which is equal to, you could probably figure it out on your own, but to this dot product. So basically each term represents a different dimension. Cube root of 3 a squared, cube root of 3b squared. Just going one term at a time. So looking at this 3ab term, that would be cube root of 3a, square root of 3a and square root of 3b, and then 1. So we ignore the 1 dimension, but once again, we just do this simple calculation in 1-dimensional space, and we get the dot product that we would have gotten if we had converted our 1-dimensional data into 3 dimensions, or 4-dimension, but the 4th dimension being a constant space, where x cubed, cube root of 3x squared, cube root of 3x would be the axes in the higher dimension. Yes, question?
So in this case, the kernel is ab plus 1 to the cube. That's the kernel?
Yeah.
And so like the whole point is to get the dot product. Is that correct?
Yes. Yeah, so it kind of, you can play around with different values of R and D. For your kernel, they're just hyperparameters. Basically, what are different dimensions that you want to project your low-dimensional data into? So in this example, in the top example, and also in this super visual example up here, we projected the 1D data into 2D, where one axis was x, the second axis was x squared. This is exactly what we did with this version of the polynomial kernel, but if we make the polynomial the degree of the polynomial 10,000, then we're projecting into 10,000 dimensional space with the corresponding axes. That's the kernel trick. Yes?
Is there a limit to which we can achieve a value? Like,
Sorry?
is there a limit? So I guess, so I understand about D, but what about R? Like, is there a limit or any huge implication if we change R drastically?
It shouldn't be a huge implication because it's really just affecting the some of the terms. So it's hard to know it in advance though. So yeah, you just play around with different values. It just changes what exactly the axes are in higher dimensional space, both R and D. So up to you to play around with more or less, and probably doesn't matter too much. So you don't want to, explore a million examples of R, or you're wasting time at that point because it probably won't make a huge difference. So last note on SVMs is that two last notes. There are other kernels as well. And just a cool note, including some which project data into infinite dimensional space, which is kind of cool to think about. And the way that ends up working is through Taylor series expansion. So I think Calculus 2 thing where each term is a different dimension, but it's an infinite Taylor series expansion. So that's basically how that works. I'll just If you don't know about that, don't worry about it, but that's via the Taylor series expansion from Calculus 2, if you do know about it. And notably, that kernel is called the radial basis kernel, which we won't talk about in this class, but it's basically the same idea, another function, kernel function that gives you the dot product in high dimension, where in this case the high dimension is infinite dimensional space because of the Taylor series expansion. So that's the first final note. The second final note is a support vector machine is, and I think I briefly mentioned it last class but didn't write this down, so the support vector machine is the support vector classifier. So we could have a hard margin support vector classifier or a support vector, soft margin support vector classifier plus the kernel trick. So these two concepts together is what makes a SVM. So that's why in scikit-learn it's called a support vector classifier, because you don't necessarily have to use a kernel that converts your data into high dimensional space in scikit-learn, in which case that would just be a support vector classifier, not a support vector machine. But if you set the hyperparameter for the kernel in scikit-learn to radial basis or to polynomial, then it's a SVM. Okay, so that's all I have to say on support vector machines. Any questions before we move on? Okay, so that's all of the, let's take a deep breath. We just went through a crash course in a bunch of different machine learning supervised methods. And we basically have learned all the mainstream ones besides neural networks. Yes, question?
Question. So, have we been using the SVMs all along this cycle?
No, that was neural networks that we have been
No.
using all along
So
for
we haven't-
logistic
we
and
haven't
linear
used it
regression.
then.
You could have used support vector machines for homework too. In last class, I think a few people raised their hands that used it. But now you know how they work if you did use them for homework too. And a lot of people use decision trees, a lot of people use random forests, and you could have used that in homework too before we covered it, but now you know how that works, linear regression, et cetera. So now you know how all these models works, and really to do machine learning, it's just the homework 2 stuff. It's just use scikit-learn, it'll take care of all of it for you, but it's important to understand how it works, if for nothing else, so you can select the right model and select the right hyperparameter, and that's a lot, hyperparameters, and that's basically what the midterm's all about, is like which model do you use when, what are the trade-offs, what does this hyperparameter mean. It's open notes, and we'll have, I think on Thursday next week, we'll do a midterm review where I'll give you a bunch of sample questions and we'll do them together in class. So you'll get a good feel for what the exam will be like during class next week. But yeah, in every machine learning class, you learn these algorithms. So now you know all the main machine learning algorithms. That's a big deal. And it's kind of like, in a computer science class, you learn how sorting works, and you learn that it's n log n, but like when you code it, you just call .sort. But like it's still important to know how sorting works in a computer science curriculum. That's kind of what we're doing here. If you're using these models, you just import the models from scikit-learn and call .fit. But it's still important to know how they work, so you know which one to use. So analogous to all the other computer science classes. So unsupervised learning is maybe about 10% of, I'm just making these numbers up, but from what I've seen, about 80% of machine learning is supervised learning, what you see out in the real world. Maybe about 10% is unsupervised learning and 10% is reinforcement learning. That might just be my bias, but that's what I tend to see out there. So that's why we spent so long on supervised learning. But we're going to talk a little bit about unsupervised learning in this class, just for a couple classes. So we're kind of moving to a whole new section of machine learning, but we won't cover it for too long because we want to then go back to neural networks, which can work for both supervised and unsupervised learning, and reinforcement learning, actually. So we'll connect neural networks to all three types of those learnings. And so unsupervised learning is, as we talked about in the first class, learning without labels. So all the models we've learned about so far has been learning to predict a label, whether that label is a number, regression, or a category, classification. But sometimes you don't have labels to predict. And so one of the types of unsupervised learning, and this is review from class 1, but just since we're starting a whole new section, good to review this, and I guess for the exam as well, where you have a bunch of unlabeled data and you want to group them automatically into different categories. So today's main focus will be on clustering. Then we'll have a break where we talk about feature selection and feature engineering, which is important for unsupervised learning, also really important for supervised learning. And the end of clustering will kind of lead into that. And then we'll finally talk about dimensionality reduction, and that might be after spring break.
So is reinforcement learning the same as self-supervised?
No, very different.
Okay. Put it up in that context. Sorry.
And so, reduction we get to on Tuesday, but probably not. Is where we have data in high dimensions and project it down into low dimensional space. Which is good to talk about because we've been talking about high dimensions with SVMs. We project it down to low dimensional space such that the distance between the data points in low dimensional space is similar to the distance between the points in high dimensional space. And by doing that, it allows us to visualize the high dimensional data in low dimensional space. I think on the first class, I also mentioned anomaly detection. You could actually do anomaly detection with clustering, or with dimensionality reduction and clustering, or with supervised learning. So I'll leave that to you to think about how would I implement an anomaly detection model using all the methods we've learned in class. Okay, so starting with clustering, we'll talk about two main clustering algorithms. And so before we get to that, what are some reasons we might want to do clustering in the real world? It's really clear why we do supervised learning in the real world. There's all sorts of things we want to make predictions on, all in every field of study and in every type of, in English, in health, in science, we're predicting things. But when do we want to group things? Well, I'll give you some examples from companies out there. So we might want to group website users into distinct categories for targeted advertising. I mean, I would never want to do that, but the big companies want to do that. And they'll pay you a lot to do that to other people. You can create recommendation systems. For example, Spotify, where they group users with similar music tastes together and recommend them the same stuff. Or YouTube, same thing, but for videos. Or Netflix, or Amazon, same thing, but for items you could purchase. You can use it to discover, so outside of the hyper, capitalist use cases, you can discover categories or subcategories in a bunch of things, but including in science, and that's what I think is cool. So, for example, of diseases, you can look at the genetic expression or the phenotypes and automatically derive new subcategories of disease. Of species, and how do we derive these phylogenetic trees? We'll actually learn about a type of clustering that's really good at that today, etc. So ... You get the idea. It can be actually used for a lot of things, and it is used for a lot of things. By far the most popular clustering algorithm is ... Does anyone know what it is in advance? PCA is a dimensionality reduction. We will get to that. Yes, k-means clustering. K-means clustering. And so we'll go through, I think I want to teach this in a similar way to the decision tree and random forest stuff, where I go through the algorithm and give you an example visually as we go through the algorithm. Do y'all like that way of learning? Okay, cool. So let's do that here. So the inputs to this model is the data itself, which is of course unlabeled. So it's just the data, just the X. There's no Y to predict. And K, which is a hyperparameter. I mean, you could call it a parameter in this case because you're not even learning parameters, so it would be fine. But we want to be consistent, so we call it a hyperparameter. And the output is a cluster assignment or a group assignment of each data point. So each data point is mapped, for example, via a dictionary or a hash map, not important, mapped to a cluster assignment. So the first step is to randomly assign K, which is the input, cluster centroids, which are the center of the cluster. The center of the cluster, and these are just randomly selected. So let's draw this first step out. So let's say we have this type of data set here, x1, x2, and we have these points over here and these points. I'm just gonna make it super obvious what the end cluster should be. Let's say we start with that data set. So the first step might be to randomly initialize our centroids. So that random initialization might be like that. Red is the centroid. 3 in this. In this. Okay. So step 2 is a while loop. So step 2, while the assignment of data points to clusters or centroids doesn't change. While it still changes, while the assignment of data points to centroids is still changing, colon, then substep. So A, we want to assign each data point to the nearest centroid. Assign each data point to the nearest centroid. We're going to draw that out. I feel like the very mathematical stuff goes at a different pace than the visual stuff, which is kind of interesting. Okay, so drawing the points from before. So we had randomly assigned these centroids. And so we assign them each data point to the nearest centroid, which in the first iteration happens to be that. And then substep B is to recalculate the centroid.
Sorry, could you repeat what the dotted circles are?
That's just the cluster so far.
Oh, okay.
So
And that's based on the centroid?
yeah.
Okay.
So assign each data point to the nearest centroid. So this would be cluster A. Does that look like an A? Probably not. Cluster A. This is cluster B. And this is cluster C. So far, okay. So step B, recalculate the centroid as the mean of the data points in each of the current clusters. So only drawing this for one iteration, but we'll, in this case, and what happens is that, so drawing the points again, and the centroids are in the same. So this centroid stays the same because the mean, it happened to be initialized right in the mean. That's kind of lame, actually. Let me make it start here. There. Now it kind of, so it started up there and then it moved into the center of the points. And this one moved to the center of the only point that it had, so it kind of overlaps the point. And this one moves to the mean of those 2 points, which is here. When you see k-means clustering written out, it still has a lot of math, but it's just like the mean of the point, so no need to do all that.
So does the actual point move?
No, I just, the centroid is on top of it.
So the centroid moves to something other than an actual point.
Yeah, it moves to the mean of all the points in the group.
Oh, the centroid's not like one of the points because he isn't.
No. It's
Oh.
Oh yeah, so yeah, that's a good point. I see how that could be confusing from how I wrote this. So let's clarify that here. These are not data points in the set. In the data set. I mean, you could make them that, but they don't have to be. Because after the first iteration, they're not going to be anyways once you start taking the mean. So might as well just initialize them to be any random point. You see that after the first while loop iteration, it's not going to be any data point unless there's a data point that happens to be at the mean of all the points in the cluster. So doesn't really matter. I mean, actually, it matters a lot how you initialize it, but it doesn't matter whether it's a point in the a specific point in the data set or not. So maybe these are not necessarily data points in the data set. Yeah, good question. And so after doing that so this two-step process, assign each data point to the nearest centroid, then recalculate the mean of the centroid, then reassign the data points to the new centroid, recalculate the mean, iterate, 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 iterate. Then finally, we return the final clusters. So it's this two-step process, which there's an important note, which I just said. So the important note, and this might be the type of thing you would just have to know for other algorithms, or think about for other algorithms for the midterm, just by thinking about how these work, but I'll be explicit about this here. The end results heavily depend on the initialization of the clusters. I mean, you could probably already see that, or if you thought about it, you can come to that conclusion. But just to show you an example, we could have, looking at the data set from before, let's draw two scenarios. X1, X2, and trying to draw the same data set. Okay, so two data sets, and let's say in case one, the randomly assigned initializations were like this, and in case two, the randomly assigned initializations were like that. We're gonna end up with very different final clusters. The first set would give us the clusters we might expect from this data set. The second one is gonna put those two what seem like they should be independent clusters all into one cluster, and do this thing where two of the data points in that third cluster are in one cluster, and that final point below is in another cluster. Here, let me just draw that. So that is a very different end result than that. And therefore, there's a bunch of different initialization strategies that are not just randomly select them, but we won't talk about that today. You could probably think of some yourself, and there's many different ways to do it, kind of with all the models we've learned about in class. We talked about the basic idea, but there's so many ways to do it, and you can modify it and see what happens. And that's basically how machine learning works, because it's not like these are laws of nature. These are just things that people made up and that happen to work. Okay, any questions on k-means clustering? Okay. So another type of clustering is called hierarchical clustering. And the goal of hierarchical clustering is similar, but it's to build a hierarchy of clusters. So goal is to build a hierarchy of clusters. And a very big use case, and y'all might know other ones, but one that I see a lot from bioinformatics is construction of evolutionary trees. So basically you have DNA from a bunch of organisms, and you apply hierarchical clustering to automatically create the evolutionary tree. These are how evolutionary trees roughly are constructed. It's actually a little bit more complicated, but let's say, we have these organisms, brown bear, polar bear. It is used in health, by the way, but I held myself back. Spectated bear. I think that's the right.
So
J-
each hierarchy is a cluster? Is that what you mean?
Here, you'll see when I do this. Giant panda, raccoon, and red panda. I think these are real animals.
Oh, yeah, red panda's real.
Okay. Dot, dot, dot. So the evolutionary tree that might be constructed through evolution, through hierarchical clustering, could tell us that brown bears are really related to polar bears, and that group together is the most related to black bears from this group, and that group together is most related to spectated bear. I think that's what I wrote, and that's related to giant panda, and maybe raccoon and red panda are more related. So I'll draw this a little bit higher. And that group is more related to this group than if we kept on going up into a bunch of other animals to the right that I didn't list. And so you've probably seen these types of trees in animal science stuff. And so, these aren't constructed actually back in the day, they were just constructed like, this kind of looks like this, so we're going to make them together. But now it's actually a algorithmic process, and it's based on DNA sequences and how similar those DNA sequences are. See, science is getting so much better because of machine learning. In my opinion, at least. I mean, maybe you could just look at it and be like, it looks close enough, let's put it together. But probably good to be objective about it. So in homework 4, you're going to use a specific type of hierarchical clustering.
So I have a question.
Yes.
Isn't this similar to like a decision tree, I guess, classifier? Because in a way, like if you kind of go down the hierarchy instead of going, up from here, it's kind of like yes, no, sort of a deal.
Kind of, but there's no labels in this case. You just have your data points.
So how do you store the information in a cluster if there's no label?
You have your data representation.
Oh.
So in this case, you might have DNA of brown bear, DNA of polar bear, etc. And you, based on their similarity, you construct this tree. So agglomerative, fancy way of saying bottom up. Hierarchical clustering, which is, I think, what one of your questions in homework 4 asks about. We're not going to cover all the material for homework 4 before spring break, so because homework 3 is still due after spring break. By the way, just since I'm on that tangent, so I updated the class website with more up-to-date due dates, and I promise the due dates, if they do change, it'll only go later, it won't go earlier. So this is the earliest possible due date, and if there's huge demand, we can move things up. But there's already, at the end of class, there's like the final project report and the final exam due, and so things are already starting to pile up. So hopefully we don't move things too back. Although the final exam's also pretty chill, like multiple choice, La Lima, so not too much work. And final project is, we'll go over, not next week, but the following week, the week before spring break, we'll break up into sections, and one day will just be 435, the other day just 635, because the final project requirements are slightly different, as grad students have slightly different goals than undergraduate students. That's the only difference between the two groups, the two classes. So homework 4 is not due till April. So Yeah, we're learning this thing that's not going to be due for a couple months, so don't forget it. So agglomerative hierarchical, I mean, we could put it on the exam, but I was thinking the exam would stop here. Does that sound good? Nothing on the exam after today? Okay, cool. So you could start.
By today, you mean like just hierarchical cluster? Just,
Yeah, or even just k-means clustering.
okay.
Cool. So it's recorded. So if there's a question on that, you can like tell me and it'll be full credit, regardless of what you put. Okay, so agglomerative hierarchical clustering. We'll do the thing again where I give the algorithm and do a visual example at each step. So the first step is that each data point is its own cluster. So I'm going to do this in a really simple case where our data is just one dimensional, so it's just a single number. And we're going to have 4 data points, 30, 35, 50. Of course, it's never realistic that we only have one-dimensional data that we want to do anything meaningful with, but for example, it works well. So each data point starts on its own cluster, and then while, so another while loop, just like k-means, while there is more than one cluster left, and there's only one step, so there's not even any sub A or subset B. It's just all we do is merge the 2 closest clusters using the mean of the data points, in the new cluster as its centroid, or the number that represents the cluster, basically. So just drawing that out here, 30 and 35 are the closest from that example, so we'd merge 30 and 35 into a new cluster, and we'd still have 50 out on its own and 120 out on its own. Then in the next step, and then the mean of 30 and 35 is 32.5, so that's the centroid of this cluster. And so 32.5 and 50 are closer than 50 and 120, or 120 and 32.5. So in the next iteration, we merge those 2 clusters. So 50 is close with 32.5, and we take the average specifically of the centroid. So the centroid of the first cluster is 32.5, the centroid of the second cluster is 50, so average of those is 42.5, and 120 is out on its own until the final iteration where we have this cluster and the 120, which there's only 2 left, so nothing to compare. Oops. We merge them, and we have our hierarchy. So that's basically all there is, except that, in higher dimensions, the distance metric becomes important, which we'll talk about in a second. But any questions on hierarchical clustering? Okay. Yeah, I think clustering is a little bit conceptually more easy than supervised learning models. Dimensionality reduction is harder, so I guess it kind of balances out. The crucial note is that, and this is a crucial note actually for all of machine learning, and it's going to lead us into feature selection and feature engineering. Okay, so we just started unsupervised learning. Now we're going to go on to this long, multi-class, but important tangent. But that's sparked from hierarchical clustering. So the crucial note that's going to spark a several class-long discussion is that we can define similarity between 2 points in many different ways. That's the start of things. It's like, how do you define similarity? And that would be useful not just for k-means clustering or hierarchical clustering, where you're taking the distance between things, or similarity, distance, same thing. But also in some of the supervised learning models we learned, most notably k-nearest neighbors, but a few other ones as well. So for example, if we want the similarity between 2 vectors or 2 data points, which happen to be vectors, as data points are always vectors, by the way, in machine learning. So if we want the similarity between these 2 vectors, we can take what we would normally think of as the distance formula, the Euclidean distance, and specifically this is L2 distance, which is just the distance formula. That's one way to do it. So 3 minus 4 plus negative 20 minus 8 squared plus 10 minus 0 squared. There's that, but there's also something called the Manhattan distance, which is also sometimes called the L1 distance, and hopefully you're seeing similarities and convention between naming for like L1 regularization, L2. The absolute value between each dimension of the data is summed up, and we don't take square root at the end. This is conceptually like if you divide your data into coordinates, how do you walk along a grid or blocks of your data to get to between 2 points? But don't worry about that here. The point is that there's many ways to define mathematically similarity, and they have many different meanings. We often have different types of data which ultimately get converted into vectors when we're doing machine learning, but sometimes, in rare occasion, not. So for example, if we have 2 DNA sequences, AAT, CCCG, y'all know that DNA is A, T, C's, and G's as a string. Yeah, so that's how we represent DNA. Our 4 base pairs. Might have been a while since you've seen that. But just tangent, that's how we represent DNA, and it's a string, and you can imagine representing A as a 0, T as a 1, C as a 2, G as a 3, so that's an easy way to convert it into a vector representation. But another way to do it, if you don't want to represent it that way, is to calculate something called the Levenshtein distance, or just because the person who invented its last name was Levenstein. This is often also called the edit distance, which is perhaps a more descriptive name. And this is a string similarity metric that's used in word processors and all sorts of things, but also in bioinformatics. And I think it's also a common like DP question that you get asked in programming interviews if you ever do dynamic programming. Just by the way, so could be a cool thing to check out if you're studying for technical interviews, but string similarity metric used in text processing and bioinformatics. I'm not expecting you to know these. It's just the point is that there's many different definitions of similarity. And on a similar note, and perhaps a even more important note, there's many ways of defining. So another crucial note that's just as crucial for machine learning, and which you probably already know, but it's good to be explicit about. There are many and perhaps infinite ways to represent data. And you can imagine that the way you represent data can affect how, and the similarity metric you use will affect how these algorithms work. You can have the same algorithm, but whether it works well or doesn't work well is based on how you represent your data and the similarity metric you use. And therefore, one of the, actually really the key area of computer science machine learning research, or at least one of the big keys, is how do you represent your data well? So I won't say the, but at least a key area of AI, not just research, but also practice, research and practice, if you want your models to work optimally, is answering how do we represent our data, because it doesn't matter which algorithm you use if your data is not represented well in a way that's informative. And how do we define similarity between two data points? So the second thing here is kind of domain specific. Like if you're doing biology, there's probably some good ways to define similarity. If you're doing computer vision, there's other good ways to do it. So we won't go into too much of that right now, but this first question is kind of key in general, and even not, it's also domain specific often, but it's not always domain specific. You know, how do you represent your data well? And so we're going to now move into two topics, actually three: feature engineering, which is how do we engineer explicitly good representations of our data, as well as representation learning, which is how do we automatically learn representations of our data, which is kind of cool. So how do we use the machine learning methods that we've learned to learn representations of our data that are going to perform well? We won't be able to get to the representation learning part till we do neural networks, because all the cool methods for representation learning are in neural networks. But we'll start talking about feature engineering, which includes feature selection. And so feature selections, how do you choose which inputs to even include? Dimensionality reduction, of course, another supervised learning method. And just plain methods where you apply an existing filter to your data to convert it. Yes, question?
So what is the Levenshtein distance? What exactly is that?
Not important for this class. It's just look it up, and it's good to know. It's again asked in a lot of programming interviews for jobs, but not necessary for machine learning.
Okay, Levenshtein.
Just look up edit distance.
Oh, just edit distance, okay.
Yeah.
Thank you.
Yeah.
Just scared me with that question, if I can hit that with an interview later.
Yes. So let's, I think with this 15 minutes, we're just going to be really high level, and then we'll start getting into specifics next class. So to motivate feature engineering, so new topic, feature engineering, very important topic that kind of applies to all the machine learning models that we've learned, because all our machine learning models take data as input, and if the data is not good, it's not going to work. So feature engineering is how do we represent our data, I guess the would work. How do we represent our data? And let's motivate this with an example. And this is going to be a highly illustrative, but hopefully educational example. So we're going to say that we're going to build an action recognition model, which is pretty, it's used in the real world. Basically, take an image of someone and what activity are they doing? Predict, are they running? Are they sleeping? Are they eating? Real world AI that does that.
You wanna do that?
Yeah, why would you want to do that? It's you could think of why that would be used. That's not for this class. Although in the fall, we'll talk a lot about that in human-centered data science, and hopefully in the spring in human-centered AI, which is different even though the names are kind of the same. And so, for example, we might have the following picture of someone. I'm just gonna draw this picture for a little bit.
So you already know what you're teaching in the fall?
Yeah, while I draw this, I can answer.
I'm just trying to think,
So-
just wondering if the schedule's out yet.
Oh, yeah, so I know what I'm teaching. I'm teaching, this is me, by the way. I hope this is accurate. I guess I should have a tablet, iPad. Yeah. And make sure you take accurate notes here. I might be on the beach, and there might be some water, and maybe a wave. And that's a shark or a wave, unclear with the drawing. And Stella, oh yeah, my dog Stella, which she's a cockapoo. Oh, by the way, my wife is going on some work trip. So how would y'all feel if I brought my dog to class? Okay. So I might bring my dog Stella to class. She's kind of a puppy, so she causes a lot of trouble, which is kind of an issue sometimes. But is anyone allergic to dogs? Okay, cool. If someone's allergic to dogs, you don't have to raise your hand, but just email me and for privacy reasons. So there might be a picture like this where the label is standing, let's say. So y equals f of x, where x is a matrix that represents that picture, versus y, and let's maybe draw kicking in this case. And we'll just do it fast. So same person, maybe frowning in this case, and maybe no gel in the hair, and arms are up and kicking, and there's a ball, soccer ball, and it's nighttime now, and there's a building in the background with windows and stars. Okay, so we're predicting standing versus kicking in this case, but a model might learn to predict basically to overfit from all these other things in the image that aren't important for the ultimate classification. So, for example, model may overfit to irrelevant features like Stella or the beach or the water or the sun or that there's a moon in this picture or stars or a soccer ball or the frown. I don't know why there's sunglasses at night in this picture, but I didn't think that through. Actually, let's. Okay, we're gonna get into technical stuff in a bit. Oh, that doesn't look like me. Anyways, so this is not a good feature representation. It's really easy for the model to overfit on the pixels. And furthermore, what if like the person happened to be on the left side of the image or on the right side of the image? Now it's learning those features. We're going to learn in neural networks ways to deal with that. But one way to do it is that we can represent our data with a better feature representation. And so, for example, we could represent this data with a feature vector that only describes the relevant parts of the data. So for example, instead of predicting on image space, we can convert all the images to, and this is commonly done in action recognition, to a set of coordinates describing key parts of the body. So I'll draw that out in a second so you know what I mean. But we might just have key point number 1 coordinates, key point number 2 coordinates, ... all the way to the bottom of the vector. And this is much less likely to overfit. So let me, this is kind of just one example, but it is a commonly used example. So aside, but still a commonly done thing in machine learning, key points is a feature representation where you take a picture of a person and you automatically convert it to a stick figure, and you get the coordinates of each of the points in the stick figure. And so if you have a way to take an input image and produce that, now all of a sudden you have a really low dimensional representation of your original data, which was highly dimensional at 1 pixel per, well, really 3 pixels per coordinate in the image, because RGB, we'll cover that more later. And each element of our new feature vector is this coordinate that describes the human body, and it's specifically not getting all of these other elements. Do you need me to write more about key points, or it's just kind of an aside, so you don't need to memorize that or anything. And there's various ways to learn key points. It turns out actually you can apply other machine learning models that predict the key points, and we might talk about that later. By the way, after spring break, we're going to get much more applied and do a lot more notebooks, but also learn about deep learning and also learn about reinforcement learning. Now that y'all know all the basic algorithms, besides neural nets and reinforcement learning. So sneak peek of the type of things we'll talk about in a bit. But this is, conceptually easy to understand, and yet it's so important. And this is, there's many cool, complicated methods to make feature representation. So this feature representation is much less likely to. The worst thing that could happen in machine learning, as I talked about, our machine learning models can learn whatever you want them to learn these days. So they're going to learn whatever you want, but ideally they should be able to generalize to new data. So there's going to be 4 main approaches we're going to cover in the next few classes for good feature representations. So the 4 main approaches that we're about to talk about include number 1, transform the data using a predefined transformation. So for example, we actually saw this before in our coding notebook on sentiment classification, the bag of words representation, where we count the occurrence of each word, and each word has a different position in the feature vector. And so just to see that example again, you know, how much would a would I don't know if that's the right phrase, but then we convert it through bag of words, which we've already seen in our coding notebook a few classes ago, and that would convert to, we'd have a position for wood, a position for chunk, a position for apple, ... and 220 for occurrence of each of those words. And that's our feature representation we put into the model. That's a predefined representation by a human. So that's one way to do it. Second approach is to transform the data using a learned representation. So for example, just showing that it doesn't appear in the sentence, and so it's
0.
yeah. So we might take our word, input it into an ML model that we learn, and that might output an automatically learned representation. Second approach. Third approach is feature selection, which we'll start talking about next class. So feature selection, where we remove unimportant inputs to the model. So we'll talk about that more next time. And approach 4, which we've talked about a lot, is dimensionality reduction, where we convert our high dimensional data into a low dimensional representation where the low dimensions only keep the important features of the original data set. Okay, any questions?
Yes.
Yes.
How do you know which features are important? Like I'm looking with some data, I've got a lot of features, but I don't know which ones are important.
Yeah, so the question is, how do we know which features are important? Well, we'll learn about that next class. There's automatic statistical ways to do it. And we'll talk about, that's the theme of at least the beginning of next class. Okay, we're at time. Thanks so much. See y'all on Tuesday.